Hi all, once again welcome back to Chemist. So today we'll have the part 10th of the question paper discussion that we were so far discussing. So I've made a change in the slide in order to make you understand that this slide actually represents the organic questions of the question paper that we are discussing. And this video is exclusively for substitution reactions in organic chemistry, and there is only one question that is included in this video. So for those who have not gone through the previous video regarding this question paper discussion, I have created a playlist in the channel. So those who are interested, you can go through. The link is provided in the iCard above. And other than that, in the last video, someone have commented regarding the online coaching classes in chemistry for Kerala PSC exam. So I do conduct such online classes, and I am planning to start a class in the month of May 2022. So those who are interested, you can contact in the WhatsApp number that is given in the description box. You can just message if you are interested and I'll be responding to it. So without wasting any time, we'll directly move on to the video. As I've already mentioned in the intro slide, that this question or this video is all about a question which is based on substitution reactions in organic chemistry, and it is the question number 36 of the question paper, and the question goes like this: which of the following reaction undergoes without formation of an intermediate? Options are SN1 reaction, SNI reaction, ARSN1 reaction, and SN2 reaction. So in order to answer this question, we need to have an idea regarding all these kind of substitution reaction. So we'll have a short discussion on all these type of substitution reaction, and finally we'll arrive at a conclusion about the answer to this question. So let's start with the SN1 reaction. I think all of you might be familiar with SN1 and SN2 reaction, because these are typical reaction mechanisms of a substitution, nucleophilic substitution reaction in a saturated carbon, that is an sp3 hybridized carbon. So in the slide you can see this is the reaction center where an SN1 reaction take place. So you can see that this is a saturated carbon, right? So this is a single bonded carbon, which is also known as the saturated carbon. So we'll have a discussion on this SN1 reaction. So this is a typical example for an SN1 reaction. So don't get confused with the phenyl ring here, because here you can have any substituent. Say it can be an alkyl group, it can be even a hydrogen atom, and whatever it is, we should bother only about the carbon atom, which is numbered as 3. So this is the reaction center where the substitution reaction is taking place. So before moving on to the question, we'll see what is the expansion for SN1. SN1 is nothing but it is substitution nucleophilic. 1 stands for unimolecular reaction. So the short form of substitution nucleophilic unimolecular is nothing but it is SN1 reaction. So when you talk about substitution reaction, it is a reaction where you substitute a bonded atom or a group with some other atom or group. For example, if you consider methane, when you substitute this hydrogen with a chloride ion, that is, when you substitute this hydrogen atom with this chloride ion, you will be getting the compound what is known as the chloromethane, right? So this is what is meant by substitution, same as substituting some atom or other group which is already present. That is what is meant by substitution reaction. Now you can actually substitute the atom which is already present with some other group. So if you consider, say for in the general case, if you consider it as X instead of halogen, if you consider it as X, depending upon the nature of X, you can have different types of substitution reactions. For example, if X is a electrophile. Electrophile is usually represented using the symbol E+. Electrophiles are electron deficient species, right? They are they usually act as reagent, or else you can have a nucleophile. Nucleophiles are electron rich species. Okay, so when you consider both these cases, when you are having a electrophile as the substituent, then that is known as the electrophilic substitution, and when you are having nucleophile as the substituent, that is known as a nucleophilic substitution reactions. I think you might have got an idea regarding the nucleophilic substitution reaction. Now you need to understand why there is 1 here. That is, you can see a superscript which is 1, which is a expansion or a short form for unimolecular, right? So what is the reason for this one? So for that we have to see the mechanism in detail. So here you can see that this is a saturated carbon and it is having a bromine atom, right? So this is the atom that is getting substituted in the substrate, and here you are having a nucleophile which is water. Water is a nucleophile because it is having lone pair of electrons on oxygen atom. So when you are substituting this bromine atom with water molecule, so as such you cannot even if you are adding water, the nucleophile is exactly the hydroxide ion or the OH minus. So when you substitute, initially OH2 will be coordinating, then it will be coordinating as OH2 plus. So I'll be in order to make you understand better, I will write here the pH, the phenyl group, we can abbreviate it as pH, and you are having a bromine group, a methyl group, and a alkyl chain here. So this is the reaction center that we are talking about. So when you are substituting it with water molecule, initially it will be coordinated as such as water. Okay, OH2. But since oxygen atom is donating its lone pair of electron, it will be definitely getting a positive charge. And from this, a proton will be eliminated so that you will get the final product as an alcohol, OH, right? So this is the alkyl group. Okay, so this is what is taking place in the case of SN1 reaction. So here you can see that there are 2 products that is possible, one with the retention of configuration and the other with the inversion of configuration. I am not going into the details of the stereochemistry of the product. We'll just consider the product formation alone. Now this is what is taking place in SN1 reaction. Now when you talk about the mechanism of SN1 reaction, it is given in this side. You can see on the right side of the slide. This is the mechanism of SN1 reaction. In SN1 reaction, the reaction actually takes place in 2 steps. That is, in the first step, it actually involves the formation of a carbocation by the elimination of the leaving group. That is, you are substituting bromine with water. Therefore, the bromine should leave. So that is acting as the leaving group. So in the case of SN1 mechanism, it is a 2-step mechanism in which the bromine atom or the leaving group will be leaving in the first step, resulting in the formation of a carbocation. You can actually see a carbocation that is formed here. So that is the intermediate that is formed in an SN1 reaction. Now in the second step, once the carbocation is being formed, that is attacked by the nucleophile, say water molecule, to form the final product. But in the case of SN1 reaction, you can see that there is a formation of a carbocation. So when you look at the structure of a carbocation, it is always having a planar structure. Okay. So that you'll study in the reactive intermediate. There are different types of reactive intermediates like carbocation, carbanion, etc. So usually this carbocation intermediate, it will be having a trigonal planar shape. Okay. So here also the same thing is happening. A trigonal planar carbocation is being formed by the elimination of bromide ion. And since it is a planar molecule, the incoming nucleophile can attack it from the above, either from above the plane or from below the plane. So both of them will lead to two different products. That is, when it is when the attack is from the above the plane, you'll be getting one product, and when it is from below the plane, you'll be getting the other product. So when the nucleophile is attacking from the same side of this bromine, you'll be getting a retention. That is a product with the configuration of the starting materials. Then you will say that there is retention of configuration. When the attack is from the opposite side of bromine, you will be getting a product which is known as the inverted product, right? So here you can see that the starting compound is having S configuration. So you can actually get a combination of both R and S product. So there is always a mixture of product that we get. One will be the product of retention and the other will be the product of inversion. Okay, so this is a very important point regarding the stereochemistry of an SN1 reaction. Now coming to the importance of substrate, the structural importance of substrate, you can actually form, I've already mentioned that during the first step of this mechanism, there is the formation of a carbocation. So when you look at the structure of carbocation, basically you are having three different types of carbocation. These are topics that are included in a reactive intermediate. That is, either you can have a tertiary carbocation or a secondary carbocation or a primary carbocation. So when you look at the stability of carbocation, the tertiary carbocation is the one which is most stable, followed by secondary, followed by primary. So always when there is the possibility for formation of a tertiary or a more stable carbocation, that reaction will follow an SN1 pathway. So that is how you make a conclusion regarding a substrate, whether it will undergo a reaction by SN1 or SN2 pathway. If it is able to form a stable carbocation, definitely it will be choosing the path of SN1 reaction, right? So here you can see that there are three alkyl halide. The importance of these, the structural importance of these alkyl halide is that this is a one which can form a tertiary carbocation. This is the one which can form a secondary carbocation. Similarly, this is the one which can form a primary carbocation. Now, when you look at the rate of the reaction, so here you can see the rate of the reaction. When there is a tertiary, when there is a substrate which is a potential tertiary carbocation, the rate is very much high. That is, it is about 1.2 into 10 raised to 6. But when it comes to the secondary and primary, the rate goes on decreasing. So you can see that if you analyze the ability of the different substrate to undergo these sort of reaction, the order is same as the stability of carbocation. Tertiary alkyl halide will be more prone to SN1 reaction, followed by secondary, followed by primary. So these are some of the important points regarding SN1 reaction. Even you are having some other points regarding the solvent, what type of solvent that you use, and I just mentioned about the solvent. So here you can actually see that there is the formation of a charged intermediate, which is a carbocation. So definitely the solvent that is more favorable for an SN1 reaction is a solvent which can stabilize this carbocation. That is a polar solvent. That is a solvent in which there is charge separation. That can actually stabilize this charged intermediate. Therefore, SN1 reactions usually prefer polar solvent. But in the case of SN2, all these things are opposite. They are exactly contradictory to SN1 reaction. So these are some of the important points regarding SN1 reaction. And the main point that you have to keep in mind is that it involves the formation of an intermediate which is a carbocation. So this is the, we can actually rule out this SN1 reaction because it actually involves the formation of an intermediate. Okay, and another point is that the stability of the carbocation is very important. So when you have a chance of forming a more stable carbocation, that will be definitely undergoing a reaction through SN1 pathway. The third point is regarding the solvent that we use. We use a polar solvent. And another point is regarding the stereochemistry of the product. We'll be getting a mixture of both the product with retention of configuration and inversion of configuration, so that you can actually say that the product will be most often will be a racemic mixture. Racemic mixture means equal proportion of R and S. Okay, so that's all about SN1 reaction. So now let's move on to the SN2 reaction. So before moving on to the SN1, SN2 reaction, I've missed out a point regarding the subscript 1. Why you are designating this reaction as a unimolecular reaction? So I need to answer that question also. So I've already mentioned, when you consider the mechanism of this reaction, it is actually a two-step mechanism. So if, for example, if we consider the general case of CR3Cl plus H2O giving Cr3OH. So if this is the reaction that we are talking about, then this actually takes place in a two-step. That is, initially the leaving group, that is the chloride ligand, will be leaving from the reaction center, which leads to the formation of a carbocation. And in the next step, the carbocation will be further attacked by the nucleophile to form the product. So it actually involves the elimination of a proton also. Okay. So these are the two steps. So when you consider the kinetics of these two reactions, this is the slow step and this is the fast step. So here you can see that the slow step is the first step, which involves the formation of a carbocation. And in kinetics, you know that slow step is the rate determining step. Therefore, when you consider the rate of this reaction, the rate actually depends upon only upon the concentration of the substrate, and it will not depend upon the concentration of nucleophile, because that is not involved in the rate determining step. So in the rate determining step, you have only one substrate or one reactant. That is why it is abbreviated, or it is considered as a unimolecular reaction. So this is the point that I missed out in the previous slide. Moreover, I would like to mention another point also. So when you talk about a carbocation, so I've already mentioned that the carbocation is having an order of stability, like tertiary is more stable than secondary than primary. But this may not always be the condition. That is because when you are having some other carbocation, like a carbocation which is having a uh, atom with a lone pair, that is, if this is a carbocation which is having an atom with a lone pair of electron. Okay, so here there can be an extra stability. That is because this oxygen can donate a lone pair, right? uh, this will be forming a double bond character, so that oxygen will be getting a positive charge. This is also a mode of stabilizing carbocation. So this does not fall into the category of tertiary, secondary, primary and all, but this is a different type of carbocation. But here also you are having some sort of stability, that is due to the presence of this electronegative atom with lone pair of electrons. So wherever there is a possibility for forming a stable carbocation, you can actually search for an SN1 mechanism. That is the thing that you have to keep in mind. Whenever you have a confusion between an SN1 and SN2 reaction, always go for a search for a carbocation. If there is a possibility of forming a stable carbocation, definitely you can go with an SN1 reaction. Okay, so that's the point that I missed out in the previous slide. Okay, now we'll move on to the SN2 reaction. Now coming to the SN2 reaction, as I've already mentioned in the previous slide, SN2 reaction is exactly opposite to the SN1 reaction. So as the name suggests, it is also a type of nucleophilic substitution reaction, but it is a bimolecular reaction. That is why it is represented by the letter 2. Okay, so this is a typical example for a SN2 reaction. So the carbon number 2 is the reaction center. You can see that here also the bromine atom is acting as the leaving group, and here you are having a even more strong nucleophile like cyanide ion. Okay, in the previous case you were having water, which is a very weak nucleophile, because in that case the carbocation was already ready. So you need only a very weak nucleophile, because that nucleophile is also not involved in the rate determining step. So that is a pretty simple one that you can have. But here this is a reaction which is very much different from SN1. So here the cyanide ion or the nucleophile, for example, cyanide ion is the example in this case. In general, if you talk about it, it is actually a nucleophile. Nucleophile is actually involved in the uh, rate of the reaction, or it is involved in the rate determining step. So here you need a very strong nucleophile. So you'll understand that point in a better way when you consider the mechanism. So it is forming the cyano-substituted product. So here you can see, when you consider the stereochemistry of the product, here you can see that there is inversion of configuration that is being taking place. Now coming to the mechanism. So initially, when we discussed about SN1 reaction, it was a two-step mechanism, because in the first step there was a possibility for forming a stable carbocation. Then in the second step, the nucleophile was attacking the substrate to form the product. In that case, you require only a very weak nucleophile. But here it is a concerted type of reaction. Concerted means it is a single step reaction. It does not involve the formation of any intermediate, but it involves the formation of a transition state. Okay, so this is the starting compound that we consider. So this substrate is written in this manner. So 2 is the reaction center, and you are having bromine as the living group, or the atom which is being substituted. And here cyanide ion or Cn minus is acting as the nucleophile. So in the case of SN2 reaction, always the nucleophile will attack the reaction center from the side opposite to the side containing the living group. And such type of attack is usually known as the rare attack. Rare attack. Okay. So in this case, the nucleophile will be making a rare attack. So I'm sorry, it is the spelling of rare is not correct. It is rare. I'm having a confusion regarding the pronunciation. REAR. This is none of the rare attack. Okay, so this is what is taking place in the case of SN2 reaction. That is, the nucleophile will be attacking the reaction center from the side opposite to the side containing the living group. So initially, when this cyanide ion or the nucleophile makes an attack, the bond between the carbon and the living group will not break. And at a point, you can see that the carbon atom of the reaction center will be bonded simultaneously to the nucleophile as well as the living group. So this is some sort of a 5-membered carbon atom, and this actually correspond to the transition state. These are partial bond that is why they are represented in a dashed form. And here the carbon atom will be having a slight positive charge, and both the living group and the nucleophile will be having slight negative charge. That is why it is represented in delta. And finally, at the end of the reaction, the bromine atom, the living group, will leave as a bromide ion, resulting in the formation of an product. So when you look at the stereochemistry, you can see that the starting compound was having an S configuration. But after the reaction, you are getting a product of R configuration. That is, you are getting an inversion of configuration. Because cyanide ion cannot attack from the side containing bromine atom. It can only attack through the side which is opposite to the bromine atom. That is why you are getting a product of inverted stereochemistry. And this the example for this one is the umbrella that is tucked in wing when it moves upside down. So you can actually, if you Google, you can see a figure like that which explains the stereochemistry of an SN2 reaction. So you have to keep in mind that there is always a inversion of configuration that is taking place in the case of an SN2 reaction. And I think you might be now having an idea regarding the reason for the two bimolecular. So here you can see that it is a single step reaction. Therefore we'll actually depend on this reaction for explaining the rate of the reaction. So when you consider the rate of the reaction, it is actually concentration of nucleophile into concentration of substrate. That is the starting compound. That is why you are having a bimolecular reaction. Okay, this is the bimolecular reaction. Now when you consider the structural importance of the substrate, in the case of SN1, we were having a more scope for a tertiary carbocation, because tertiary alkyl halide, because it can form a very stable carbocation. But in this case, no carbocations are involved. And another point is that when the nucleophile is making an attack on the reaction center which is having the living group, there is the possibility for steric hindrance. So when you move from primary to tertiary, the steric hindrance at the reaction center goes on increasing. So that makes the attack of the nucleophile more difficult. Therefore, the order of reactivity in the case of SN2 reaction is like tertiary less than secondary less than primary. So the primary is having the more reactivity according to SN2 reaction, because in the case of primary the steric hindrance is very small. So you can actually, that is reflected in the rate of the reaction. Approximate rate goes on decreasing when you move from primary to secondary alkyl halide. And moreover, when you talk about the solvent that is used for this analysis, here it doesn't involve the formation of any charged intermediate. This is not a charged intermediate because these are delta charges which cancel out each other. So this cannot be considered as a charged intermediate. Transition state is not an intermediate. Therefore, all the other substrate or reactant species are neutral species. So these are or organic compound. These are organic compound. Alkyl halide, they have least solubility in polar solvent. Therefore, the solvent that we usually prefer for an SN2 reaction are non-polar solvents. Non-polar solvents like DMSO. DMSO and DMF are not that non-polar, but compared to water, they are non-polar, etc. These are some of the solvents that are mostly preferred for SN2 reaction. So the important point regarding SN2 is regarding the reaction, that is a single step reaction involving a transition state. There is no intermediate, no formation of intermediate is taking place in SN2 reaction. The second thing is about the stereochemistry of the product and regarding the structure of the starting material. So the primary will be having the more tendency to undergo SN2 reaction because it can form a stable carbocation. It can provide a reaction center with less steric hindrance. Okay, that's all about SN2 reaction. Now coming to the third type of nucleophilic substitution on saturated carbon, it is abbreviated as SNI reaction. I stands for internal, that is substitution nucleophilic internal. So you are having only a typical example for this one. This is the only example that you can have for this type of reaction, which is chlorination of alcohol with thionyl chloride. Okay, so when you want to substitute this OH minus with a chlorine, you can actually go for the reagent which is known as the thionyl chloride, which is SOCl2, and it is having some advantage that the byproduct are gases, so that the recovery of the product is very easy when you use this type of reagent. You can actually use some other compound like PCl4, PCl3, PCl5, etc. for chlorination of alcohol, but SOCl2 is preferred over these kind of catalysts, this reagent, because it is having the byproduct as gas, which is very easy to remove from the product. Okay, so that is the importance of SNI reaction. So whenever you are using thionyl chloride for chlorination of a alcohol, then or conversion of an alcohol into alkyl halide, the mechanism that usually take place is designated as the SNI reaction. Okay, so here you can see that this is the substrate that we are talking about. This is the reaction center that we have, and when it reacts with SOCl2, this OH minus, the lone pair of electrons on the oxygen atom, that is making a nucleophilic attack at the sulfur atom of the thionyl chloride, so that the chloride ion is leaving as a ligand. So this is the alkyl chlorosulfite intermediate that is being formed in this reaction, and this will then undergo a bone cleavage. That is, this bone will cleave to form a carbocation plus a negatively charged anion, and that is known as the intimate ion pair, because you are having a combination of both positive and negative ion. And this will then further eliminate a sulfur dioxide molecule to form the chloro alkane. That is, this is a general case, so we can say that it is a chloroalkane. And here you can see that there is always a retention of configuration. In the case of SN1 reaction, you were actually getting a mixture of both retention and inversion, and the final product is a racemic mixture. In the case of SN2 reaction, you are getting an inverted product, and in the case of SN1 reaction, you are getting a product of retention of configuration. That is, the product will be having stereochemistry same as that of the starting material. So this is the only example where you can get an SNI reaction. So in this case, we are actually designating it as an internal reaction, because here the nucleophile is actually, so if you consider this portion, the nucleophile is actually present inside the molecule. That is why it is designated as internal or SNI reaction. Now another example for, it's not the another example, it is about the mechanism in detail. If you consider the decomposition, or else you can consider it as a different example. So because here you are having an alcohol, here you are having a substrate which is known as the alkyl chloroformane. So in this case also you can have a similar type of mechanism where there's the initial step, which is the slow step, that involves the formation of an ion pair, which then eliminates a molecule of carbon dioxide in the fast step to form the final product. Here also you will be getting the retention of configuration. So these are some of the examples where you can have an SNI reaction. These reactions are very rare, so you cannot get more number of examples. So this is, I think this is fine for explaining the mechanism. These two examples are more enough or good enough. So we have already gone through the substitution reactions in saturated carbon, which was SN1, SN2 and SNI mechanism. Now we have the one of the other option, which is the AR-SN1. As the name suggests, AR, it represents an aromatic system. So that is a mechanism that is usually followed by an aromatic system. So for that reason, we'll have a short introduction or short discussion on reactions of aromatic compound as well. So when you consider an aromatic system, a typical example of an aromatic system is definitely benzene. There are two possibilities. Either you can have a substitution reaction or an addition reaction, because it is having double bond. But aromatic system, they usually don't undergo addition reaction, because addition reaction will affect the aromaticity of the compound, which is a extra stabilizing factor. So they don't usually undergo addition reaction, but they can undergo substitution reaction. And in the case of saturated carbon, we have discussed about two different types of substitution reaction. Either you can have an electrophilic substitution reaction or a nucleophilic substitution reaction. Similar to that, aromatic system can also have a electrophilic substitution reaction. That is more probable for an aromatic system because it is electron rich. So it usually undergo a reaction with an electrophile, which is an electron deficient species. So this is the general representation for the electrophilic substitution of a reaction. This is benzene. This hydrogen atom is being substituted with an electrophile, and this usually requires the presence of a catalyst, which is a Lewis acid. Now coming to nucleophilic substitution reaction, this benzene or other aromatic system, they can also undergo nucleophilic substitution reaction, but that is very rare and it requires the presence of some important reagents and all. So for the time being, we'll consider the mechanism of electrophilic substitution. It also proceeds through two different steps. In the first step, the electrophile will make an attack on the benzene ring or the aromatic ring, um, causing a disturbance to the uh, pi electrons, and this will lead to the formation of a carbocation. And in the next step, a base will be there. That is, I've already mentioned that you require a Lewis acid or a base, and that base will abstract a proton to retain the aromaticity again. So this will form the substituted benzene. So this is the mechanism of electrophilic substitution reaction, and you are having two steps. In the first step, electrophile will be added, resulting in the formation of a carbocation. In the next step, the carbocation will be a proton from the carbocation will be abstracted by the base to form the final product. Now, when you consider the different electrophilic substitution reaction that is possible for benzene, either you can have a chlorine substitution, that is known as the chlorination. This is the electrophile, this is the reagent that you use, and you can just go through the slide for the different electrophiles that are possible and different types of electrophilic substitution reaction. So that's all for electrophilic substitution reaction. Now we'll see in detail the nucleophilic substitution reaction. Now coming to aromatic nucleophilic substitution reaction, there are four different types of mechanism that are possible. Either you can have an addition elimination mechanism, and that is abbreviated as ARSN2 mechanism, or you can have the opposite type, that is elimination addition mechanism. That is a famous mechanism which is also known as benzene mechanism, since it involves the formation of a benzene intermediate. Now the third one is ARSN1 mechanism, which is actually given in the question, and the fourth one is known as the radical nucleophilic mechanism or SRN1 mechanism. Okay, so these are the four different types of mechanism possible for nucleophilic substitution reactions in aromatic system. So for the time being, we discuss only the one which is given in the question, that is ARSN1 mechanism, and that is given in this left side of the slide. A typical aliphatic SN1 reaction that you know, that we have already discussed, you'll be having a leaving group. Leaving group leaves the system to form a carbocation, which is then attacked by the nucleophile to form the final product. But coming to ARSN1 reaction, this is not possible. That is, the formation of the phenyl cation is not possible. That is because the phenyl cation is not stabilized by any electronic effect like resonance effect. Therefore, this reaction, that is an ARSN1 reaction, is not possible with all the aromatic system, but it is possible only with the benzene diazonium salt. So when you are having benzene diazonium salt as substrate, you can expect an ARSN1 mechanism. Okay, that is because in this particular case, it gives an extra stability to the phenyl carbocation. So this is the mechanism of the reaction. In benzene diazonium salt, you will be having N2Cl or N2 plus ion attached to the phenyl ring. That is what is known as the benzene diazonium salt, and that initially it eliminates a molecule of nitrogen to form the phenyl cation. So you will be having other substituents as well, which is shown as R in the figure, and this will then further on addition of this nucleophile will form the final product. So this you have to keep in mind that this mechanism is possible only in the case of benzene diazonium salt. For any other substrate, you cannot get this type of mechanism. And another point is that this mechanism is also known as Untitled mechanism and vicarious nucleophilic substitution as well. So this is all about the aromatic nucleophilic substitution reaction through ARSN1 mechanism. If anybody is interested to get an idea regarding the addition, elimination, addition or radical nucleophilic mechanism, you can just give a comment in the comment box. So I'll be considering it for the next video. So now coming back to the question, now we are in a position to answer this question. So the question was about the substitution reaction which undergo without the formation of an intermediate. So in the case of SN1 reaction, you have already seen that it involves an carbocation intermediate. And in the case of ArSN1, you have a phenyl carbocation. In the case of SN9 reaction also, you are having an intimate ion pair as the intermediate. But in the case of SN2 reaction, you are not having any intermediate because that is a concerted reaction which involves only the formation of a transition state, not an intermediate. Therefore, the answer to this question is definitely SN2 reaction. So that's all for this question. So that's all for this video. Thank you for watching. And if you like the video, please do subscribe and share. And I'll be coming soon with the next part soon. So stay tuned for the next part. Thank you.